Our naive algorithms for sorting n objects required this many steps, so they were big O of n squared. Is this fast enough? No. Suppose we need to sort 1 million records. A computer that can perform 1 billion operations a second would require about 8 minutes to sort through all these records, and a million record database should be considered small. Our goal is to create better algorithms. The good news is that it's very easy to learn everything you can be taught about being creative. The bad news is, this is it. You cannot be taught creativity, but there are some strategies that will allow you to develop it. A useful one is known as divide and conquer. In divide and conquer, we take a problem and divide it into smaller instances of the same problem, conquer, that is to say, solve the instances, and then somehow glue those solutions back together. Let's try it on the sorting problem. If we have n elements to sort, the obvious starting point is to divide this into 2 sets with fewer elements. We can then sort each set individually, then merge them back into the original sort. This leads to an algorithm known as, well, we need a good name for what we do. What are we doing? We're merging things and they're sorted, and yeah, let's call this merge sort. Now remember, lather, rinse, repeat. While we could do this, notice that in the conquer phase we need to sort 2 smaller steps. So we have the same problem we started with, which will have the same solution. We'll divide each set into 2 sets with fewer elements, then sort each set. And if we lather, rinse, repeat, we end with singletons, sets of 1 element, so we can't go any further, and now we need to figure out the merge step. So how many steps will it take to merge them? It's convenient to imagine we're reading the first element of each set. We need to make a decision which of the 2 current elements is smaller. We'll put the smaller into the merge set, then move the reader. So how many comparisons do we need? Imagine that the set elements are indexed x1 through xk and y1 through yk. Initially, we'll compare x1 and y1. One of these is added to the set and the reader is advanced. Note that regardless of which one advances, the corresponding index will be increased by 1. This means that in the coarse bar comparisons, the sum of the indices will go from 1 plus 1, because we're comparing the first elements, that's 2, all the way up to k plus 1, where since we increment after the comparison in preparation for the next, we allow an index to go to k plus 1, even though there isn't actually a k plus first element. And so this means we'll need a total of 2k plus 1 minus 2k minus 1 comparisons. Now, if this isn't clear, remember, concrete never hurts. For example, suppose we're merging 2 sets of 2 elements. We'll compare the first elements, then the first element of one with the second element of the other, then the second element of both, for a total of 3 comparisons. And our formula tells us that 2 times 2 minus 1 is 3, so the formula seems correct. So suppose we have n equals 8 elements. We'll break this down into 8 sets of 1 element, then merge them back. Merging 2 sets of 1 will require 1 comparison, and we'll need to do that 4 times. Next, we have 4 pairs. Merging 2 pairs of 2 elements will require 3 comparisons. And we'll need to do that twice. Now we have 2 sets of 4. Merging the 2 sets of 4 will require 7 comparisons, and we'll do that once. So altogether, we need to merge 4 pairs of sets of 1 element, taking 1 step each, merge 2 pairs of sets of 2 elements, taking 3 steps each, merge 1 pair of sets with 4 elements, taking 7 steps, for a total of 17 steps. In comparison, our other sorting algorithms would have taken 28 steps, so merge sort is about 50% faster. Or is it? Since we're splitting the sets until we get singletons, let's assume that we're starting with n equals 2 to the power k elements. Then we'll need to merge 2 to the power k minus 1 pairs of 1 element, taking 1 step, 2 to the power k minus 2 pairs of 2 elements, taking 3 steps, 2 to the power k minus 3 pairs of 4 elements, taking 7 steps, and so on, eventually giving us 2 to the power k minus k 1 pair of 2 to the k minus 1 elements, taking 2 to the k minus 1 steps. And this takes, to find the sum, so consistency counts. Note that the number of elements in a set can be expressed as a power of 2. So let's rewrite those as powers of 2. And another useful guide, don't do arithmetic. We determined that the number of computations for a set with n elements is 2n minus 1. So instead of computing the number of computations, we'll leave the formula. So if our set has 2 to the 0 elements, we need to perform 2 times 2 to the 0 minus 1, 2 to the first minus 1 steps. If our set has 2 to the first elements, we need to perform steps, and so on. So we'll need to merge 2 to the power k minus 1 pairs of 2 to the 0 elements, taking 2 to the 1 minus 1 step each. 2 to the power k minus 2 pairs, taking 2 to the 2 minus 1 steps each, and so on. This means if we have n equals 2 to the power k elements to sort, we'll need to perform. Now if we add these all up, notice that we have k factors of 2 to the power k, and then we're subtracting a geometric sequence that consists of powers of 2. And so we can simplify that as now if we have n equals 2 to the power k elements, then k is log n to base 2. And so k times 2 to the k is really n log to base 2 of n. And so for n elements, merge sort will take us n log n to base 2 minus n plus 1 steps. Remember that a computer that can perform 1 billion operations per second would have taken about 8 minutes to sort 1 million records using our naive sorting algorithm. But if n equals 1 million, then merge sort requires about 20 million steps, and at 1 billion operations per second, this would take 1/50th of a second, which is far faster